First of all, I would like to thank the organizer for inviting me. It's really a great honor for me to be here, and I will give an overview of what interferometry has taught us the past decade for young massive stars. I'm an ESO fellow, and basically I'm going to focus a little bit more on what near-infrared interferometry has taught us about young massive star environments. This is the outline of my talk. First, I'm going to give some general background on massive star formation and why do we care about MY-SOs. And then I will continue with presenting the main advances that we learned via interferometry. And in particular, I'm going to focus on accretion and ejection information through dust and gas. But also another topic of high interest that was also presented from Emma before about binarity and what do we know about binarity in MY-SOs. And I will continue with the conclusions in some future direction. So first of all, why massive stellar objects? As we know, massive stars are really influential objects. They influence the dynamics and chemistry of entire galaxies. Yet it's been decades already that we don't quite understand how they form, especially the past decade. It has been a topic of high debate and interest to understand how these stars come to become so massive. So if one wants to actually understand that, has to go to the earliest phases of star formation, of massive star formation, and this is where the massive stellar objects are. So by massive, my definition of massive is more than 8 solar masses. So these objects are known to be undergoing accretion as well. Yet they have been quite a challenge to observe, and this is because of multiple factors. These are the most crucial ones. They are highly embedded sources. They are optically invisible. They are short-lived compared to the LOMA stars, but also nature just prefer to produce more LOMA stars. So the high mass stars are rare, and also they are located quite far away, so with typical distances of several kiloparsecs usually. So how are we going to observe them during formation? We know that disks are quite important in star formation in general, especially in LOMA star formation has also taught us that disks are quite prominent. And this is an environment we also want to trace with high mass stars. Basically, this is a sketch of what we know happens around LOMA stars while they're forming, how is the accreting environment. And basically here I just want to show that it depends what kind of wavelength and technique one is going to use. You're going to retrieve a different information from different parts of the disk. So for example, ALMA does great in tracing cold disks around forming stars. But basically this is where the outer disks, mostly outer disks, but also where the major mass reservoir is located, and can reach scales of hundreds of AU. Then if one wants to go to a bit more energetic processes and a bit tracing disk structures that are closer to the protostar, you have to go also to a shorter wavelength. So for example, mid-infrared is great in tracing planet-forming regions of tens of AU scales, but when the actual accretion takes place, and this is something we're really interested, this is something that can be traced in a hotter, shorter wavelengths. Basically, this is where the near-infrared interferometry becomes really, really crucial. So with near-infrared interferometry, we can trace scales sub-AU to AU. And again, this is a scaled version, a scaled down version, because this corresponds to low mass star formation. So it's safe to assume that when we have to do with high mass stars, we can expect a bit scale up version from this one. For this talk, I'm going to focus on these two aspects, as I said before. So let's start about what we get to know the past decade about accretion and presence of disks. And first, I'm going to focus on dust. So why, before going to the observations, why are disks important in massive star formation? So why do we think they're actually there, and why we're so obsessed in trying to observe them? This is because since we know that massive stars are there because we have observed them, but it has been a challenge to understand how they form. So theoreticians came up with a model where disks can play a crucial role. The difficulty to understand massive stars is because the high radiation coming from the central object is expected to halt the massive inflow. And therefore, the models say, okay, if you have a disk structure around, it can solve a lot of challenges because you can basically get rid of a lot of angular momentum, which could be problematic. The disk self-shields against radiative acceleration, but also most of the radiation can escape in a direction perpendicular to the disks, allowing further inflow. So basically, you have also the presence of outflows there. So the past years, there is more and more information about large-scale cold disks around massive young stars. Here is an example of ALMA, a 1.2 millimeter emission towards a massive forming star. It's an excellent example. In my opinion, it's very beautiful as well to look at. Very clear disk structure, very nice observations, which were followed also from more work in millimeter regime of the spectrum, where gas tracers could also show Keplerian motions. So basically, the millimeter observations have started showing us more and more that there are disk-like morphologies and Keplerian-like structures, disk structures around massive young stars. And by that, we are tracing tens AU to thousands of AU scales, because by definition, this is what ALMA can actually trace. Again, this is a cold material. So what do we know about the hot material? So here is where the near interferometric comes to play. There is an excellent example, pioneer work back in 2010 from Stefan Kraus, where it was the first time that we saw AU scale hot disks around massive stellar objects, and that was really, really exciting. This is the first image reconstruction that could be obtained towards an MYSO at 2.2 micron emission. And then this was followed by about a decade of silence. And this silence is basically demonstrates what I said before of how really, really challenging those observations are and how deeply embedded those objects are. So gravity has to come to advance our understanding even more. So basically, this was a work published from Gravity Collaboration led by Karati in 2020, where there was another example of a hot disk surrounding another MYSO. Basically, these are some continuum observations and models that they were able to trace those disks. More recently, we were able to get such observations, K-band observations of 6 objects using gravity. And basically, this allowed us for the first time to actually get direct sizes of the K-band emission, but also to place them in the size luminosity diagram. So this is the size luminosity diagram. This is the ring radius, basically, of the disk over luminosity. And here is where the new MYSOs are located. The shaded lines correspond to different models of where one expects that dust sublimation to occur. But what I would like you to take out of this plot is that the inner regions of disks around stars, young stars in general, it doesn't matter their central mass, it doesn't matter if you are a low mass, intermediate, or a high mass object. It seems that your inner sizes are going to scale with the square root of the luminosity. So basically, these new data points here correspond to MYSOs, extend what was previously found and reported from Milan Gabbett for the intermediate and low mass stars. So this is an important finding by itself, but also kinds of confirm that indeed hot disks are there, are present and prominent for high mass star formation objects. So moving on, with the more disks around MYSOs, there was recently published a very important study in a multi-wavelength approach as well. So in this study, they were able to simultaneously fit the spectral energy distribution, the MIDI interferometric data, and physicomics images at around 20 micron towards 8 MYSOs. And 8 is an amount of MYSOs to have such a comprehensive study that really advanced our understanding of this object. So yes, I cannot say enough for it. So the radiative transfer model consisted of a disk outflow envelope morphology. So here is an example of an object of how they fitted the SCD, the MIDI, and radial profiles of the images. And here is just also an example of how detailed one could go to these models, because basically they tried even to include substructures of the disk. And here we can see an example of how a model of no substructure performs worse than a model with a substructure for this specific MYSO, not for all of them. So by this approach, they were able to actually set important constraints, which are many, but the ones that I would like to focus here is the disk inner and outer sizes. So basically, if there was a presence of inner holes, they were able to trace that. The cavity opening angle as well, but also density and temperature structure, and the presence of substructure, as I just described, they were able to see if it's there. So they went a bit further with this work, with a follow-up paper in the same year, and they used some near-infrared spectroscopy in order to classify the evolutionary status of these objects. So they said, okay, these are the near-infrared spectra. We have some characteristics that we can use in order to say if they are type 1, 2, or 3, with type 1 to be the earliest state. And that was basically of some diagnostic likes of H2 emission, for example, bracket gamma, and some iron transitions as well. So what they found is that they found a decreasing density with evolutionary state. They found an increasing cavity opening angle as the star evolves, and also an increasing inner dust radius. So basically more holes as the massive star evolves during its formation. Also, interestingly, the more evolved the object, the more substructure it had a tendency to show. So when I saw this, coming from a background myself of Loma star formation, it reminded me of this. So basically, this was something that proposed from Arts Sarge in 2006, and then it was also confirmed observationally how Loma star form. Basically, you have highly collimated outflows that they widen in angle as the star evolves. And I hope you agree with me that the resemblance is very clear of what's happening with HIMA star as well. So a major outcome from this work is that massive disk outflow evolution follows a very similar path as Loma's disk outflow evolution, regardless of the fact that the type scales are quite shorter when it has to do with the HIMA star formation. So now I would like to move to accretion and disk as traced with CAS. One very powerful diagnostic tool that we have been using for that is the bracket gamma emission. So I would like to go through what we can learn from studying the bracket gamma emission. First of all, it traces hot gas, so 10,000 of the UK, and it is associated with accretion in young stellar objects. We know that from several studies. Its exact origin is unclear. So here, again, you see a sketch of what we know about the environment of a young stellar object while it's forming. And the bracket gamma has been a bit problematic to attribute exactly where is the location. So some people have proposed that it comes directly from accretion, some from this wind, extending wind or outflow, or even jet. So this powerful diagnostic line, we think that it's also something we can trace very well with MYSOs. And luckily enough, it is present spectroscopically for all MYSOs that we are aware of. So we are able, by trying to trace it spatially, to try also to understand what are the innermost gas that exists around MYSOs as well. So the gravity observations of these 6 MYSOs I mentioned before that we were able to place in the size luminosity diagram, we were also able to determine the size of the emission. And here I present the radius of the bracket gamma over the continuum over the luminosity. So there is not a specific trend with the luminosity, but I think what becomes apparent here is that for all MYSOs, they tend to have a smaller bracket gamma emission compared to the continuum, which means that it originates from a region closer to the protostar than the dust. Another information we could get from that, from closer phases, was that it was not only smaller, but it happened also to be coplanar with a disk. And this information combined can tell us that probably we are dealing with some disk wind or a base of a jet origin, as also can be depicted from this sketch here. And it's not the first time that people have seen something like that. There is also very important work from Davis 2010 and Karate 2016 on the topic. And I encourage you to have a look on those papers too. When we come to talk about gas, not only the bracket gamma is a very powerful tool, but also the C over tone emission has been proved in the past to be doing great in actually tracing the innermost gas environment of disk. It has been found spectroscopically with modeling that can trace small-scale gaseous disks originating from a region innerwards compared to the dust. And also the motions, there were coplanar motions there that show that basically comes from disk. So this is a bit more clear where the origin of the CO comes from. So this is an example of the first example. It's the only example from first specially resolved CO Bathian emission towards an MYSO. That was again from gravity collaboration, the paper I referred before, led from Karate. And here is the line profiles of the CO. And here are also the visibility curves for different position angles and different baseline configurations. The colors are the observations and the black line are the models. So basically what was found there that the CO emitting region is located in the inner gaseous disk, well within the dusty rim and pointing towards the disk accretion as we know it, as we suspected. So here is a bit of a sketch of how we think this environment is. So I would like now to pass to the binarity. So binarity in high mass star formation. First of all, thank you to Emma because you also gave a great overview why we're interested. I'm going to pass a bit faster. So we are interested in studying them because they do have a significant influence on high mass star formation and evolution. We know that the majority of them, when they are more evolved, massive stars, are found to be in tight binaries. And also, we know that we are not doing great in observing them during formation because, again, very challenging thing to do. There are different proposed formation mechanisms. I don't want to go into detail what each one proposes, but what I would like you to take out of it is that it depends what kind of proposed formation mechanism you are going to study. You are going to get a different properties for the form binary. So for example, some theories predict wider binaries in opposition to others that they are predicting more compact, and also with the different mass ratios as well. So observation input is really, really important on that aspect. And how do we observe them? There are different ways to observe them, from aero imaging to spectroscopy. Here, I would like to focus on long baseline interferometry because this is the topic also from the talk. With long baseline interferometry, we can trace closed binaries, and by close, I mean AU scales. In the past decade, there were some serendipitous discoveries of tight massive protobinaries. Nothing was quite targeted in the sense as a survey because it was not really possible. Here, just a few examples demonstrating what VLTI has done in the research of studying tight massive protobinaries. So we used the 6 MYSOs in the study of gravity, and we thought, okay, let's do some primary statistics to see how many of these objects can actually be modeled with a with a binary configuration. Here, I plot binary fraction over massive stars at different phases of evolution, from bedded MYSOs to pre-main sequence and main sequence objects. And what we can see in this plot is that it becomes a bit apparent that it seems that the binary fraction increases with evolutionary states, which could be quite promising result. Yet we need to really increase the amount of objects in the sample in order to be sure that this is what is happening. So at 2 to 300 AU scale trace with a interferometry, with a near-infrared interferometry, this is about 17%, and it's also in agreement with what was previously found for other MYSOs in larger scales using imaging. So I would like to pass to some conclusions. I hope I have convinced you that interferometry has done a lot and has contributed a lot in our understanding of how massive stars form. We now know that disks exist. They are present and very prominent in high mass star formation from AU to thousands of AU scales. And it's very similar to the environments that we see towards low mass stars. The innermost part of the disk seems to scale with the square root of stellar luminosity independent of the mass of the young stellar objects. It doesn't matter if they are massive, intermediate, or low mass, which is also nice to see. Moving on, the high mass protostellar evolution seems to follow similar geometrical patterns to low mass protostellar evolution. And by that, I mean, we see an increasing outflow, opening angles, inner holes, and substructure as the objects evolve. The near-infrared interferometry through bracket gamma, I suggest a disk with disk accretion for MYSOs, but this is something we still have to confirm. And MYSO binaries at 2 to 300 AU separations are present, but maybe a bit less common than massive main sequence stars on similar scales. So if I have time, I can move with some future direction. So we would like to get more direct size measurements for a larger sample of MYSOs. K-band and gravity plus will prove to be, I think, provide really promising results. So I would say stay tuned for the next years to see what gravity plus has to say about this environment. Simultaneous feed of spectral energy distribution, interferometry, and near-infrared spectra, and in particular, the bracket gamma emission CO and sodium is necessary to form a more detailed picture of those innermost regions. Multi-wavelength imaging campaigns, I think it's really the step forward. We are lacking images of those environments, and that's important not only because we want to show some pretty images, but also because they are crucial in proper characterization of the environments, to determine the disk and binary properties, also to investigate further the origin of the model substructure. If there is a base, or what kind of environment is responsible for the substructure. For distinguishing between disk width and jet origin, high spectral resolution will be an asset as well for proper kinematic modeling. And of course, we would like to explore young massive binary statistics at a larger number of MYSOs. And this is again where Gravity Plus can contribute a lot. That's it. Thank you very much for your attention, and I'm happy to take questions.
Thank you very much for the nice talk. Any question from the room, the whole. Yes. Please tell your name.
Hi, it's Gail Schaefer from the Char Array. So I had a quick question. How would you go about explaining why the binary fraction increases going from the young massive stars to the main sequence stars?
That's a great question. Thank you. So I think if we fully trust this result, and if it can be confirmed with more objects, of course, I think it can point towards a hardening of binaries through evolution rather than forming in situ. So this would be a theory that would support what we see. But again, I think we really have to be careful on claiming at this point, because with 6 only objects, it's a bit tricky to make conclusive remarks on that.
Thank you. Other questions from the whole? Also from online. Then let me have a note that you describe actually the disk evolution as a similar process than what we see for the lower mass cases, that with time actually the envelopes somehow becomes more dilute, and then opening angle of the outflow cavity widens and so on. But actually from the low mass regime, we know that this is not a simple, smooth process, because there are some cases, which there were several talks in the morning, this large outbursts of the young stars, which according to some models actually widen, for example, this outflow somehow push away for a while, temporarily, this envelope, which comes back at the end of the outflow. And now we know that in some cases, high mass stars produce very similar outbursts at eruptions. So maybe in generalizing, this is the evolution what you described, but for shorter period, it may be interrupted by some deviations from that.
Yeah, thank you very much. It's a very solid remark indeed. And I think we're a bit far from, in the massive star formation, at least studies, observational studies, to be able to trace smaller scales in order to see episodic accretion, for example, or episodic ejection and so on. But this is for sure something that we should focus on in the future, to see in a shorter time scales how the characteristics changes between one phase to the other. But I just want to show that from not knowing what's happening in this environment, that we see such a similar evolution, even though, as you said, probably it's not going to be as smooth as the one I presented. But yeah.
Thank you. More questions? Yeah, Stefan?
Yes, Stefan Gross. When we study the multiplicity fraction for the different ages, I was wondering whether there's a risk that we might miss some companions for the younger ages just because of contrast issues, right? Like if you look at main sequence binary, you might spot a very high contrast companion, while for the embedded ones, it's more difficult to find these. So is that corrected for this effect?
So no, it's not corrected. And again, this is exactly a very valid point we are also discussing on the paper. Indeed, somehow it seems that Pioneer can perform a bit better in actually detecting binaries and having the correct contrast. Also, it depends how embedded those environments are. Of course, some information can be missed compared to something which is not as embedded. And so getting multi-wavelength information, because in this approach we just had the gravity observations, so something we are pursuing is to obtain also Pioneer observations, and then hopefully with having 2 filters there, one can get a bit more solid constraints if the binary is really, if a companion is really there or not, and also constrain also better the flux ratios, or yeah, what's the exact configuration of the binary, and exclude or include more companions if they're present. So I think the multi-wavelength approach is very important when it has to come to the very embedded stages that you can be missing information because of the wavelength.
Okay, thank you. Well, if there are no more questions, then let's thank Evgenia and actually all speakers of the afternoon again.